allowed to bring it.
Can we test with people online? Do we?
Sorry, there are people watching online. So
that's one. And the recording.
Okay. So on either side of the dislocation, we notice an area that is depleted or region that is depleted in arsenic. So what this suggests is that the arsenic enriched in the dislocation was sourced from the regions adjacent to it. So this points to the dislocation impurity pair model where arsenic is being attracted to the core of the dislocations. And so, for our enrichment model, we said that the remobilization of arsenic occurred through diffusion. So we start with arsenic that is already in solid solution within the pyrite crystal lattice, and deformation introduces defects, dislocations. These dislocations attract the arsenic within its core as they're migrating through dislocation creep processes, and this leads to the enrichment of arsenic along low-angle grain boundaries or subgrain boundaries. Now, unfortunately, I was not lucky enough to find gold in my samples, but a different group out of Curtin University in Perth was luckier than I was. And a couple of years later, they published this great paper showing the same process occurring in pyrite from another orogenic gold deposit in China. So not only did they document gold within dislocations along a low-angle grain boundary, but they also documented other critical metals such as nickel, copper, and bismuth. So what's important here is that these material characterization techniques really allow us to understand how metals become enriched in sulfide minerals. And that's not only important to, but basically by understanding how these deposits form, this allows us to refine our exploration efforts to find more, so we get to take less invasive exploration approaches. But beyond that, it's also important to know how these metals occur, because it might have different implications for optimizing metallurgical processes to extract the metals. Okay, so now that we've talked about segregation in ore minerals, we'll move on to a slightly different concept, looking at voids in geomaterials. So basically, if you think of a void, or the simple definition of a void is any space or volume that is unoccupied, or at least where the solid phase is absent. So this can be either a volume occupied by vacuum or a volume occupied by a fluid. And as you know, the presence of voids in materials can have both detrimental and beneficial effects on its properties. So for an example of a detrimental effect, when we have vacancies in our material, these vacancies can coalesce, forming voids. These voids can also coalesce, and this can eventually lead to mechanical failure of the material. However, we can also intentionally introduce voids into different materials to enhance their properties or introduce wanted properties. For example, of beneficial effects, we have the presence of voids will greatly reduce the density of a material. We can also increase the compressive strength of materials. And there's also a whole bunch of other properties that can be enhanced with introducing voids. Now, voids are also commonly present in geomaterials, and they can occur in various forms. So we have porosity. So this is usually the empty spaces in a rock. If you consider sedimentary rocks, for example, specifically sandstones, we have a whole bunch of sand grains that are consolidated together. But the spaces between these sand grains sometimes will be occupied by cement, but sometimes it'll be completely empty. So we have a lot of porosity or void spaces in sedimentary rocks. We also have commonly voids in the form of fluid inclusions. So these are small microscopic droplets of fluids that are included or trapped within a mineral during growth. They can also occur post-growth. For example, if you have a fracture in your mineral that then heals, so you can also trap fluid inclusions there. And then lastly, we also have voids present in magmatic rocks, specifically as volatile filled gas bubbles. So for this case study that I want to discuss today, we were testing the hypothesis that fluids, whether it be present in pore spaces or in the form of fluid inclusions, that these fluids can have a weakening or softening effect on mineral rheology. So this has been thoroughly documented in quartz or quartz-rich sandstones, for example, where wet sandstones have much weaker and much softer than dry sandstones. And this weakening mechanism typically can occur in different ways. So we can have hydrolytic weakening where the fluids transform the strong silicon-oxygen bonds within the quartz to form hydrogen bonds, and so these are much easier to break and facilitate flow. Then we can also have enhanced volume diffusion. So by having more fluids present in your minerals, you're introducing oxygen, you're maximizing oxygen density, you're introducing point defects, and this can result in faster diffusion. And then lastly, you also have dissolution reprecipitation, where fluids will dissolve minerals at regions of high stresses and reprecipitate them in regions of low stress. But for this specific project, what we wanted to look at was fluid inclusion. So we wanted to see what the effect of fluids in the form of fluid inclusions, how does it affect the rheology of sulfide minerals. So once again, we looked at naturally deformed fluid inclusion-rich polycrystalline pyrite, also sampled from deposits in the Abitibi subprovince. And we wanted to see how does the pyrite deform in the presence of these fluid inclusions. So once again, we started with EBSD. And what we noticed is that there appeared to be some crystal plasticity within some of the pyrite grains. And if we look at this higher strain area in EBSD, we also notice or document some low angle grain boundaries or subgrain boundaries. But when we take a closer look at them with ECCI, we notice that these subgrain boundaries were mostly microfractures. But we did still, however, document that there were some low angle grain boundaries that are propagating from these microfractures. So based on this information, we can tell that the pyrite is deforming mostly brittly, but there is some minor accommodation by crystal plastic deformation. So for this specific case study, we also prepared atom probe tomography specimens based or along one of these subgrain boundaries that propagated from a microfracture. So this is the 3D reconstruction of one of the specimens that we prepared. It's a bit more complex than the last reconstruction I showed you. So we have the distribution of iron in pink. And then we have these arsenic and oxygen isosurfaces. So these isosurfaces simply represent envelopes around a specific concentration of that element. So in simple terms, these blobs represent regions enriched in arsenic and oxygen. And if in this data set, the fluid inclusions are documented as these high density clusters of arsenic and that are rich in arsenic and oxygen. It may sound counterintuitive that a fluid inclusion or a void is documented as a high density feature. This is all due to the fact that during when we have imperfections on our specimen tip, we have artifacts that are created by field or ion trajectory aberrations during field evaporation. I could show a whole presentation just on those aberrations, but to confirm that these were in fact fluid inclusions, if you look at a composition profile through them, you see that they are also alkaline rich. So we have sodium and we have potassium within these inclusions, which are typical of the hydrothermal brines that are present in these deposits. But more importantly, not only do we document the fluid inclusions, we were expecting to document the fluid inclusions, But what we notice is that most of these fluid inclusions, or some of them, are linked by these arsenic-rich dislocations. And again, I wanted to confirm this. So we went to TM, prepared a lamella, and we noticed the same features. So we have fluid inclusions in these darker circles. And then we notice that these fluid inclusions are linked by dislocations. And it's important to notice here that the dislocations have this bowed configuration. So based on this observation, or these observations, we came up with a fluid inclusion induced hardening model for our pyrite. So basically, in our first stage, we have migrating dislocations during deformation. And once they encounter the fluid inclusions, they become pinned. So once the fluid inclusion or the dislocations are pinned on either edges by these, once the dislocations are pinned by fluid inclusions on either ends, they can't really move anymore, except for the core of it can still migrate. So this is what leads to this bowed configuration. But then, since these dislocations are linked to arsenic-rich fluid inclusions, we have pipe diffusion that starts to occur. So the arsenic diffuses from the fluid inclusions into the dislocation cores, and this further immobilizes the dislocations. So this will lead to local hardening and therefore will promote brittle deformation in the pyrite. So these results actually contradicted the initial hypothesis that fluids always have a weakening or softening effect within minerals. Okay, so the third process I wanted to talk about today is precipitation hardening. So similar to the previous hardening model that I showed, so precipitation hardening is, some of you know this process better than I do, but basically when we apply a heat treatment to a softer material in order to strengthen it. So this heat treatment will create precipitates within the material, and this acts as obstacles for dislocations, leading to strengthening. So the example that I'm showing here is a specific case where we applied a heat treatment on an iron-based alloy that was doped with other elements, including titanium, molybdenum, and vanadium. And we induced the nucleation of coarse shell nanoparticles through this heat treatment. So the way this works is the material is heated, and then during subsequent cooling, the material goes through a phase transformation from the high temperature FCC structure to the low temperature BCC structure. During this phase transformation, we start to get the precipitation or the nucleation and detachment of precipitates along this moving boundary. So this leads to equally spaced planar arrays of precipitates within the material. Now, as I mentioned, these precipitates act as obstacles for migrating dislocations. And the only way that dislocations can overcome these obstacles is through the Arowan mechanism, which is when they bow around the dislocations and then continue to migrate, or they can migrate through dislocation creep or during creep. Both of these processes, however, require large amounts of stresses, and therefore they lead to hardening. Now, the next case study that I want to show is how precipitation hardening occurs in the continental crust. And before I get to this specific process, just wanted to give a bit of background on earthquakes, and you'll see why this is relevant. So earthquakes happen on one of two major settings on Earth, either along plate boundaries or within faults in the continental interiors. And what you can see in this graph here is that the earthquakes that occur along continental interiors are associated with a lot more fatalities. The reason for this is not that they're larger earthquakes, it's that continental interiors are more densely populated than plate boundaries. But regardless of this, even though they pose a great risk to society, we still don't fully understand how earthquakes nucleate and propagate in the deep continental crust. And the main reason for that is because the lower continental crust has higher temperatures and should behave more ductily. Therefore, any earthquakes that would have happened at depths within the continental crust would have been completely overprinted by later ductile deformation. So to really understand how mechanical failure can occur at depths, we need to look at microstructures in stronger minerals. And one of these minerals is garnet. So for this particular project, we were looking at mechanisms of mechanical failure in garnets, and we specifically sampled garnets that had been that were from the exposed lower crust in the Musgrave province in Central Australia. So once again, we started with EBSD. And so the three figures shown here show the orientation or the pole figure map, the misorientation map, and a grain boundary map. And what we notice is that we have a micro shear band between two garnet clasts. The grains within this shear band have very low misorientations or low internal strain. They show scattered orientation of the grains, and they are delineated by high angle grain boundaries. So from this, it kind of looks like it's subgrain boundary rotation. But if we take a closer look at these grains in BSC imaging, we notice that a lot of the subgrains are once again microfractures. So this is more likely indicative of cataclasis. However, some of these grain boundaries or high angle grain boundaries have this curved shape to them or lobate shape. So this suggests that even though the grains or the microshear band formed through cataclasis, it subsequently recrystallized through grain boundary migration. One more important detail here is that the high angle grain boundaries have a very bright contrast. So this suggested to me that there might be some sort of chemical segregation along these boundaries. So of course, I prepared another atom probe specimen. And this is probably still to date my favorite data set so far. It was completely unexpected. And what we noticed is that, so this is the distribution of iron ions. And iron seemed to form these planar arrays, regularly spaced planar arrays of iron nanoclusters. So this is very similar to the precipitation hardening example that I showed you earlier. Therefore, based on this observation, I came up with a precipitation hardening model for garnet within the lower crust, where during recrystallization, the grain boundary is migrating, and as it's migrating, iron starts to segregate along the grain boundary. Then once the boundary becomes fully saturated, it will start to precipitate iron in the form of nanoclusters. So if this process continues, this is how you're left with this regularly spaced planar arrays of clusters. And if, as in the metallic alloys, these clusters act as obstacles for dislocations, we can also lead to dislocation entanglement at these clusters and potentially lead to microcracking. So this hardening mechanism potentially can explain mechanical rupture in the lower crust and might be related to deep seismicity. Okay, so now the last process I wanted to talk about is also related to earthquakes. So this is dissolution reprecipitation in materials and geomaterials. So dissolution reprecipitation is a process where a solid phase is being dissolved by a fluid and reprecipitates a new phase. So this process can either occur due to changes in the physical or chemical environment. And in the case of the physical environment, this is usually driven by stress. So we can have dissolution along faces with high stresses, and then the mineral reprecipitates along regions of low stress. But it can also be chemically induced. So if you introduce a fluid that is in disequilibrium with the current or the minerals that are present, the fluid can dissolve the minerals and reprecipitate a new phase that is in equilibrium. So in this particular project here, we wanted to investigate the weakening mechanisms related to earthquake rupture. And to do this, we looked specifically at ultracataclastic veins from the granodiorite in Naxos. And we targeted these ultracataclastic veins because they are fault rocks that have previously been linked to seismic friction. So the exact mechanisms by which earthquakes or rupture occurs in rocks is not very well understood. But what is generally accepted is that rupture is usually driven by this leading process zone. So here. So where you have a zone where you have defects, including pores and microcracks, and eventually these defects become interconnected, allowing for rupture to propagate. What's not well understood is how do we even create these defects? How do these microcracks form? And so this was the goal of our most recent project. So here we looked at an ultracataclastic vein that terminated into an orthoclase mineral or orthoclase clast. So orthoclase is a potassium-rich feldspar, and it's one of the dominant minerals in the continental crust. Taking a closer look here at this fracture terminating in the orthoclase, we can see that there appeared to be some other finer grained phase that we thought might have been albite. So to confirm this, we did EDS and we did BSC imaging of the fracture. And yes, we could confirm that they were in fact a different phase, maybe not specifically the albite composition, but slightly more calcium enriched. But what's important here is that the boundary between these two phases along the microfracture is a cuspate-lobate boundary. So this is very typical and very indicative of dissolution reprecipitation. So in this case, we would have a more sodium, slightly calcium-enriched fluid that would come in through the orthoclase crystal. It would dissolve the orthoclase and reprecipitate as albite. What's important here is that the boundary between orthoclase and albite is a semi-coherent boundary. So this leads to elastic strain accumulation at the boundary and can lead to microcracking as well. And we do have evidence of microcracking at this boundary between the two phases. What we didn't quite expect, however, is if the only responsible mechanism here is dissolution reprecipitation, then we should expect to have a host control orientation between the parent phase and the daughter phase. But the newly recrystallized albite had a range of, and a fully scattered range of orientations. So this led us to propose a feedback loop during rupture where we have the continuous interaction between cataclasis and dissolution reprecipitation. So think of it as you initially have a fracture. This fracture allows fluids to circulate through the minerals, dissolving the orthoclase, reprecipitating as albite. Then this resulting incoherent boundary between the two phases leads to microcracking, which allows further rupture of the fracture. However, then during a subsequent rupture event, we then break up the newly precipitated albite, which then rotates and then allows for fluids to percolate even further through the fracture and continues the whole feedback loop. Okay, so I know this was a lot of information in a short period of time, but my goal here was not for you to follow every single step of this presentation and understand everything thoroughly, but I wanted to at least give you some examples and show you that the concepts and the theories that you study in material sciences do apply to geomaterials as well, and they do help us to understand larger scale tectonic processes. What I think needs to happen even more is we need to develop more collaborations, more bridges between material science experts and geologists or earth science experts. And so this is why I think this Characterize at UBC effort is really great, and I think we can really push the science further if we continue to do so. And just quickly, I thought I would mention our lab. So Filter is the FIPKI laboratory for trace element research at UBCO. It started off as a very small lab, but we're now recruiting more people. We're buying a lot more instruments. We have a new test can Clara, hopefully getting here next summer. But But yeah, so we have facilities for ICP spectrometry, SEM, electron microprobe analysis, micro XRF. So if you're ever at UBCO, even though you have everything you need at UBC, you're always welcome to use our core facility.
Although we have everything at UBC, we have a sample going into the facility for some characterization for XRF.